You can see my screen, right? Yes, no?
Yes, sir.
Okay.
Yes, sir.
Okay, so let's get started. So this is where we were. We were talking about analog and digital transmission. Just hold on a second. And this is where we ended. The digital transmission. Oh no, wait a second. Yeah. Analog transmission, you use amplifiers to boost signals, amplifies noise. Digital, on the other hand, use repeaters, which kind of extracts the bits and then resends it with the normal power. So it's, you extract the bits, remove the noise, resend it. So noise is not amplified. So which is why longer distance is possible, because if you travel longer distance with analog signals, then you will put amplifiers in the middle, more than one amplifier, and then the noise will keep on getting multiplied, and so on. And more distortions will happen. You cannot take them out. So what you need to remember is basically almost all long distance communication nowadays is digital. That may carry analog data like voice and video and so on, but all long distance communication nowadays is digital. Okay. Long distance is a relative term, but it's anything more than a few kilometers or something is considered to be long distance. This is also something that you need to remember. The equipment wise cost and all also is lower. This third bullet, higher degree of multiplexing, we'll talk about it later on a little bit. And as you know, if it's the digital data, then you have standard techniques for encryption and so on. Okay. So mostly all long distance communication nowadays is digital. Okay. Okay. Let us talk about something else. So what is the channel capacity? So channel is basically that, this communication path between a sender and a receiver. So what is the maximum data rate achievable for transmission? So data rate is what? Rate at which data can be communicated. Since we are talking about digital data, where we transmit bits, once again, recall that we are talking about data. So we kind of distinguish between data and signal. What is finally being carried below, maybe analog, digital, etc., and different types of signals and so on. But at the top level, for the information that I want to send, I just look at bits of something, 110, whatever, basically. Okay. So it's measured in bits per second. So ultimately, whatever data I want to send, that may be a file, that may be a digital video file, that may be a audio converted to digital, whatever. If I look at that file, which is a bit pattern, what is the number of bits I can pump out in there? Okay. So your data rate is bits per second, but the signal rate is the number of signal components per second. So this is again the signal thing. So what do you mean by that? So as I said earlier also, suppose I use only two signal levels, 0 volt and 5 volt. So I say 0 volt is my 0, 5 volt is my 1. Can be other way, anywhere up, basically. Okay. Then if I transmit, okay, this pattern 1010, okay, this is what the 1010 pattern will go like. So the rate at which the signaling rate is nothing but the rate at which the signal changes. Okay. So in this case, there is a one-to-one mapping. So the rate of change of signal is the same as the rate of change of data. Okay. Because one signal level, 5 volt signal component, 5 volt, 0 volt is carrying 1 bit. But I told you that I could have done this. Okay. This complicates other things, but I can say 0 volt is 0, or not 0. 0 volt, I use 0. I use a 3 volt, 6 volt, 9 volt. Just suppose. Now that I have 4 voltage levels, I can say this will encode 0, 0. This will encode 0, 1. This will encode 1, 0. This will encode 1, 1. So now, if I want to send 0, 0, 0, 1, just suppose 0, 0, 1, 0. Okay. So I will have a 0, then 0, 1, so I will go to 3 volt. Okay, then 0, 0, so I'll come back to 0. Okay, and then 1, 0, so I'll go to 6 volt. Okay. So my signaling rate is actually low, basically, because I have just made two transitions. Okay, 0 to 3 to 0, 6, but I have transmitted more data. Okay. And this is kind of obvious, or we'll come to that later on. So this is, let us not use the word baud. Baud was used more in the context of all these things. So number of signals, each signal component, in this case, this 3 volt, 6 volt, 9 volt, etc., can represent more than 1 volt. So data rate actually can be greater than signaling rate. Because by changing from 3 volt to 6 volt, okay, I have actually sent, so this is just one signal transition, but I have actually sent 2 bits, basically, one signal. Okay. So this is a thing that, again, it's more appropriate for analog signals, and then there's a repercussion in digital also. But Nyquist sampling theorem is something that you should all know. Okay, it's very interesting. Again, most of these things, as I will summarize hopefully at the end of this class, some of these things will be already done for you as a computer scientist, but then some of the things you should know. So just think that this voice thing, okay, is an analog signal. So if I give you an analog signal, okay, so this is a nice perfect sinusoid signal basically, okay. But if I give you any analog signal, okay, you can break it up into frequency components, you know that. So you will have different frequency component, F1, F2, etc., etc. Okay, and then it may be infinite, but then you know that you can always say this is the part that if I transmit only these components, it's going to be more or less the same out there, because these parts will have very little signal power. So even if they get cut off, it's okay. So depending on what this range is, you may transmit all the frequencies, or you may transmit the part which is the high signal power, most of the signal power concentrated. But then this is an analog signal, okay, whatever the signal may be, and I want to finally transmit, as I said, over long distance, I want to transmit 0, 1s and so on. So how do I convert this signal, okay, from analog to digital? Okay, so Nyquist rate comes into one part of it. So you cannot definitely send a continuous signal. So what you do is sample the values. Okay. Now, question is, what is the rate at which you sample? If you sample too low, if you had this and this sampled here and here from these 2 points, it's impossible to know that this has happened. But if you sample too many of them, then obviously you can do that. So what is the optimum rate? Because if you sample too many of them, more than necessary, then you are transmitting too many things. So that will take up your bandwidth. But if you transmit too few, then the signal cannot be reproduced from there. Okay. So Nyquist sampling theorem is the very, very famous theorem which says what should be that sample rate. It says find out the maximum frequency of the signal, sample at least at the rate of 2f. At least. Okay. Usually we sample a little higher. Okay. So if I do this for this, okay, let's say this peak value is 10 volt, just suppose, I'll get different things. So basically I will get values like this, okay, time versus voltage values basically, minus things and so on. All right. So I got a discrete signal, no longer a continuous signal. Now that's not part of sampling theorem, but if I want to digitize this, basically I look at, each of these values. So maximum is 10 volt. I say I will take, a 4 bit. So my 10 volt will become, 1010, and then appropriately I will code the other ones, and then I will transmit this. On the other side, I will take out these 4444 patterns, and then I will reproduce the values. I'll get a signal like this, and then I will kind of regenerate the signal from there. Are you with me? Yes, no? Hello?
Yes, sir.
Okay.
Yes, sir.
So Nyquist sampling theorem says simply any signal, this is a nice sinusoid we have done, but any signal if the maximum frequency component is f, you can sample it at rate at least 2f. If you do that, then you will be able to reproduce on the other side. There's a lot more detail, the signal perfectly. Now, as I said, some signals will have infinite bandwidth, in which case you look at the effective bandwidth, which is where most of the signal power is concentrated. Now that basically base. So this is an analog signal. This gives you a discrete signal. But then we don't want to transmit so many different values. We could have. That's still a digital signal. Okay. So typically what we do is we quantize it. Basically, we kind of map this to whatever these different values, whatever some things, okay, number of bits, and then we transmit them. So this is what is, you don't ever have to design this, I'm sure, what is called an ADC, an analog to digital converter. You sample, quantize, send the quantized bits basically. Again, this you're not expected to know this. Okay, I'm just saying this is what ADC, DAC things are. There's similarly a digital to analog converter. Okay. So that is Nyquist sampling theorem. Okay. And then the other question we say is what is the capacity, maximum data rate that I can achieve over a channel. Okay. So this is what Nyquist bandwidth says. Nyquist bandwidth says the maximum data rate C that you can achieve over a noiseless channel. But remember, that's a perfect situation. Remember, we said at least thermal noise or white noise will always be there. So we'll see how to handle that. Okay. So if you have C, then this says 2 into B. What is the bandwidth? What is the range of signals that the medium, whatever channel you're talking about, passes with less attenuation, and then log to m bits. So m is the number of discrete signal levels. So as I said, if you use only 2 levels, okay, then you have only one this thing. If you have 4 levels, you can do 0, 1, 1, 0, 1, 1. So each can carry 1 bit. If you have 4 levels, can carry 2 bits and so on. Right? When we do encoding, we'll see, because these levels you cannot increase indefinitely. You cannot say 8 levels, 10 levels, and so on. Then you will need huge power, and the gap between the powers will decrease too much, and your cost will increase like anything. Okay. So when we do encoding, we see what are the techniques people do. At least I will mention them, so they know the names and so on. So this is what Nyquist says. Take a channel, know its bandwidth, know what is the scheme that you are using, how many signal levels. So 0 and 5 volt, this will be just 2 signal levels, okay, and then compute this. But this is for a noiseless channel. What if there is noise? So you can look up this computation. These are straightforward computations from here. So Shannon extended so these two theorems, Nyquist bandwidth and Shannon's capacity formula, or Shannon's law, as it is called, are extremely important. Very well known things. So these are things, as I will explain in the end of the class also. It's not that as a computer scientist or you will have to work with too much. Okay, but again, it depends on what level. I should not use the word work with much. Normally, if you work at the higher layers, okay, normally. But then these are things that people expect you to know. So when until you get into the real world for 10 years or something, people will say, so what will be the Shannon capacity and so on. Okay? Definitely in time fibers and all, so be prepared for that. Okay, so this says, so that was for a noiseless channel. Okay, this is what about if I consider thermal noise? So this is Shannon's law, which says the maximum bit rate that you can achieve is again B, the bandwidth, and then signal to noise ratio. So this is not in dB, this is plain signal power by noise power. Okay, so the idea is this, that if there is more noise, okay, remember this is kind of white noise, so this is kind of uniform. There is no spikes or anything basically. Okay, so this is not going to happen for thermal noise. And we use thermal noise because, as I mentioned in last class, that's what we know how to measure predictably. Okay, so I can actually a priori talk about how will it affect the channel and so on. All other things will depend on what you are carrying and so on. Okay. So even if you have 2 wires going, Okay, if both of them carrying 0 voltage, nothing will happen. Okay, but if one of them carries 0, one of them carry 1, they are very close together, electrical conductor, then this will affect something and add something and so on. Okay. So all the other types of noise that you have seen, intermodulation, etc., will depend on what you are actually sending, how you are going to use it, and so on. Whereas this one will kind of depend on just the room temperature, basically. So let's not worry about how to measure it. It's there in the book also if you want to read, but let's not worry about it. But this is something that we can measure predictably, thermal noise. So the idea is very simple. So how can I increase the capacity? One way was, as we saw, as in like the earlier one, I can increase this M. Okay, because B is given. Okay. The other way I'm saying that when I talk about noise, okay, then the noise level I can circumvent by increasing the signal power. So if there is more noise, if I increase the signal more, this quantity will increase and my data rate will go up. And that is intuitive. Okay. If I have a higher signal, there may be noise, but the noise will not affect me much. Okay. The signal power will dominate over the noise power. So this is the, but the other side is the theoretical maximum capacity. All right. So these are the two formulas that link the capacity in bit rates, bit per second of a channel. How do we use it? You start with, what is the signal that you're going to send? White noise you can calculate. So you say, theoretically, what is the maximum that I can achieve? Okay. So suppose you have, I don't know, B is equal to 100 megahertz. Okay. Then in some system, you calculated noise, you know what is your transmitter power, that power you will transmit. Let's just suppose this is 5. Just suppose. I'm saying arbitrary values. Okay. So you say my maximum capacity is 100 into 1 plus 5. So what is log 6 basically? Somewhere 2.5 or something. Just rough basically. Okay. So I'll say this is 2500 Mbps. So this is basically theoretically the maximum that you can reach with the signal power that you are using. And then I will take this back to Nyquist and I say I'll put this here. I know the B, I'll solve for M to say, in order to achieve that, how many signal levels do I need? Okay, so I will now put 2500 Mbps here. So this is 2 into 100 megahertz. So mega will cancel and log 2M. So your log 2M will become 2500 by 200. So that is approximately 12. Okay, 12.5 of course. So, and then your M is 2 to the power that basically. Okay. No, 12, yeah, right. Okay. But then you see 2 to the power that is a huge quantity. So this is what it says is theoretical business. So usually your M will be much smaller. So this is the theoretical. You will never be able to achieve the theoretical. Almost basically. Okay. High, but then again I may have to make some small calculation problem, but you get the idea. So I compute the theoretical. Okay. Theoretical is too high. But to calculate the theoretical, I need to know what is my signal power that I'm going to use. So with this signal power on this channel, okay, theoretically, what is it that I can use? Given the noise, white noise. And then I take it back to Nyquist criteria and say, fine, to achieve that theoretical that I've computed, what is the number of signal levels that I use? 8. And typically what happens is this signal level you will find to be very high, quite high. And that many levels cannot be used. So you reduce, and that's why you cannot really get the theoretical maximum thing. Because now to get that same SC, you need to work on the C. Is it clear? The business of channel capacity? Yes, no? Hello? Can you hear me?
Yes, sir.
Yeah. See, answer some just a yes, no. Okay. See, I know you were looking forward to the class, but trust me, this semester is really bad for me because last semester and all you were prepared for the online class. This semester we were all, really looking forward to stand in front of you. I don't know about all. At least I was looking very much to stand in front of you, use the board, which have not been used for a long time. Okay. So try to be a little bit more interactive. At least say the yes, no's, and so on. Helps me. Okay. All right. So we looked at kind of little bit ad hoc fashion, as I said, some of the important terminologies, things that you will encounter. As I said, data communication is like a full course. Okay. But some of the important things that people may ask you about, and some of the things you know, and what is the bit rate? We'll talk about BPS all the time, signal. Okay. When we do encoding, we'll talk about signal. So you need to know about that. Okay. Then this capacity, all the standard things. For the rest of this class, we'll go to the other side of communication. It's a transmission medium. Okay. And this is kind of more information. Okay, what kind of mediums are there, what is there, and so on. So I'll go through this somewhat fast. There's not much to say, but then at the end of the class, I will summarize and say kind of what is there, what should you be, in practice right now. So these are the parts where in the offline class I had this. I have in my office, somewhere basically. I had collected optical fibers to pass around the class for you to see, and so on. Okay, but anyway, no point seeing it on the camera and so on. So transmission medium is that medium over which the signal will propagate. And we classify it over two classes, one called guided medium. This kind of the signal is guided over there. So this is basically the wired medium that we talk about, or unguided. That's the term for wireless medium. So unguided means it's not guided along a path, so it can spread. Whereas guided medium is will stay close to the path. There will be small, radiation from there and so on, but we can control that with other things if we want. And in a practical setting, the key concerns are data rate and distance. So we'll see different types of medium can support different data rates, and depending on the attenuation that they suffer and the other distortions, there's a maximum distances after which you must place a repeater for those things. Okay, rough distances. So we'll see. So look at the other point, which is what I'm going to do at the end of the class a little bit at least. Okay, so when you choose your medium, you need to be aware of what is the data rate the medium can support, and what are the maximum distances they can go, so you can kind of estimate your cost of putting repeaters and so on. Okay. What are the things? Bandwidth. So we'll see every medium. We talk about the bandwidth of the medium. Okay. So bandwidth, as we know, is finally the signals that it is able to pass, the range of frequencies of the signal that it is allowed to pass. Okay. With very low attenuation. And this is kind of obvious. If I get higher bandwidth, I can give higher data rates. Okay. So if this is just a very layman's example, if this is the signal finally passing, carrying some data, okay, then the frequency components, range of frequency components for this, okay, and if I pass this is going to be large. And again, I'm talking about the range of frequencies in which the maximum signal power is concentrated, because both of them will have actually infinite number of frequency components if you do Fourier analysis. But then you will see most of the frequency signal power concentrated, that effective bandwidth that has to pass, that is needed for this to pass, is going to be much higher than that for obvious reasons. Okay. So then the medium that is carrying this should be able to pass this, otherwise there will be distortions. So higher bandwidth medium gives higher data rate. And then other thing we say, what is the attenuation? And this is usually measured in decibels per kilometer. So this says what is the data rate that you can achieve. Okay. So this affects the data rate. This affects the distance over which you can take it. Okay. And then third is the interference. which is linked to distance also, like, what is the interference out there? Somewhat linked, but there's other issues also out there. Let me go through the medium. You will understand. For each of them, we'll kind of show you what the medium is, what is transmission impedance, what kind of interference can happen. So this is kind of the electromagnetic spectrum. The ones that I want to look at is this and this. Rest of them, it has radio, AM radio, FM radio. It's a nice picture. It's their installings. Okay. So this entire transmission medium part is in chapter 4 of Stone's. Okay. The part that was covered before that is in chapter 3, and this part is in chapter 4. So twisted pair, which is what your LAN cables are, is around this range. Okay. So that is around 1000 megahertz max. Okay. Here that also depends on the type of this, because twisted pair are different types of twisted pairs. Because optical fiber, if you look at this, okay, is in a huge range. Looks small, okay, but this is not a linear scale. Okay. So this is a large thing. Okay. So if I want to pass, that kind of immediately tells you, if I want to pass very high frequency signals, okay, then I will go for an optical fiber. I'll summarize at the end. Whereas if I want to pass low signal thing, again low is a relative thing, I'll kind of use twisted pair. Coaxial cable you will see in the textbooks and all, but they are no longer used for computer network communications. Even though in my office, I have a very old office, I still have a coaxial cable point. Okay. So when we do LANs, we'll talk a little bit more about this. So these coaxial cables are like, your cable TV cables basically. That's basically a coaxial cable. Okay. But they are no longer used. So if you do not know about it and somebody asks you, so why don't you know coaxial cable? You can safely say they're no longer used in networks. So I did not know it. Okay. So as I said, guided, there is this. This is there. Again, I'm saying so that you know the name if somebody tells you, but this has not much relevance for computer networks now. But this was a very important, this was the original cable for kind of building local area networks and all. And this again a table taken from this. Again, I kind of want you to, you have words that you will not understand now, not needed also. Okay. This one and this figures out here a little bit. Okay. The frequency ranges you see. So let's forget about coaxial cable. This is like 3.5 kilohertz, 1 megahertz. Okay, you will see something more as we have seen basically. Okay, this is kind of a little bit old, but look at the optical fiber thing. It's in terahertz basically. So look at the range of frequencies that it can pass. There's a hidden question here that nobody is asking me, but that's okay. You may not get that question immediately. Maybe later on I will talk about it. Okay. And from a practical point, if I want to use, nobody uses twisted pair for 2 kilometers even nowadays, unless you really have to. I'll tell you why. You can, but usually, okay, much less than that. Again, I would not say use the word nobody uses, but usually over 2-3 kilometers, you don't want to use twisted pair. Okay. But look at this optical fiber thing. So the repeaters that you have to space, put in like kind of at 40 kilometers, tens of kilometers. Don't take 40 as a sacrosanct thing. Don't take 2 as a sacrosanct thing. So this is like 1-2 kilometers. This is like tens of kilometers. It will depend many things on the different types of optical fiber. And typical attenuation. Attenuation, remember, we know the attenuation is basically depends on the frequency. So typically this is what the attenuation is. Okay. But there will be other factors in twisted pairs as we'll see. So this is more data. Twisted pair is twisted pair. It's basically 2 pairs of wire twisted together. Okay. So basically this is like a normal electrical wire, kind of, not exactly the same material wise, but looks like that, and then they are twisted. If you just cut open your LAN cord once, okay. Yeah, I know, don't cut open your LAN cord because that will cost you. But again, I think you understand a twist, and this twist length is very important. Okay, so higher the twist length, lower is the interference. Basically, it's kind of interference here and interference here is kind of cancels out. Let us not go into the electrical side of that, but this twist length is very important. These are all specified by standards. Okay, so you don't just twist arbitrarily. And usually a LAN cable, for example, typical LAN cable contains 4 of these twisted pairs. So there's 4 pair cables, 8 cables out there. And as I said, low frequency transmission over short distance. Pros, they are very cheap. They're lightweight, thin wires, easy to work with. Okay, relatively low bandwidth, data rate. Okay, at the end I will talk a little bit more. Shorter range. Again, we have seen that. Susceptibility to interferences noise. This is plain electrical signals, so unless you shield it properly. And remember that plastic coating is not the shield, okay, because that has nothing. That cannot take away your electrical interference. Basically. That is more a physical shielding. Okay, so shield does not mean that plastic coating that you see on top of the wire. Basically. And it has an attenuation problem as with any other medium. So the ones that you see most often, LANs and DCs, as I said, is unshielded. Just because you see a plastic thing on top of that doesn't mean shielded. Okay. I would not use the word ordinary telephone wire. I thought about cutting it earlier. Cheapest, easiest to install, but then there is no shielding. So if you run too many wires side by side, this will have electromagnetic interference. You do shielding or twisting and all to reduce that, but you will still have it. And shielded, what it does, let me show a picture that will be good. So this is a plain unshielded. So this is your UTP. Okay, you have cables and then just plastic coating on each of them. So this is not a shield, one second. Okay, so this will have interference, but I twist each of them to have reduce the interference between these two. Okay. Now, shielding comes in different ways. This is the first level of shielding, which says individual things are not shielded from each other, so they will still have interference, but I will put a foil shield or screen. So this is called a foil twisted pair. Okay, you don't need to remember all the names. UTP is what you need to remember. This is the name that you will see most of. So outside interferences are reduced, inside interferences are still there. And then you have something like this, okay, where each of them are shielded, and then you have a foil out there. Okay. So it's a matter of how much, what environment you're putting it, how much interference you expect. And very, very important, I have not talked about it at all so far. In any design, never forget the cost. You can always build things with the great choices and so on. But then the cost is there. So you need to worry about the cost. Okay. So you have unshielded twisted pair and shielded twisted pair. And these things come from standards. There are organizations which make electrical standards for cabling, LAN cabling, different types of things, different organizations. Too many of them for. Okay. So these are the terminologies you need to remember. Cat3 is no longer used for computer networks. Most of the older buildings will have Cat5. Older means semi-old buildings, now 10 years, 20 years old, will have Cat5, Cat5. Okay. So common in LANs up to 1 gigabit. So this bandwidth up to 100 megahertz, smaller twist length, maximum distance 100 meters. So these are just numbers that you need to remember. Little bit. Then you go to Cat6, the bandwidth increases, max distance, but then it can bandwidth increases mean it can support maximum data rate. Okay. But then the distance will decrease. I'll talk a little bit more about distance in just few minutes, 5 minutes maybe. Then Cat6A, increase, then you have 7, 7A. Okay, so they have standards. So you will typically see Cat5, 5E, 6. Modern buildings are all made with Cat6, the new ones coming up. Okay. Older buildings will still have Cat5. So you won't see Cat3, 6, 6A also. 7, 7, 8 are costly, so unless you have very specific needs for them, you don't really use them. In contrast, the optical fibers, okay, very, it's a miracle of technology, okay, not miracle, but it's not miracle, but what I meant to say was, you just imagine how this is built, okay. But then what it does, we are not going to that. So you have basically a thin path through which light can go, and you have two layers, and you have the refractive index is different. So this light, okay, doesn't get the internally reflected out here. That's the idea of this thing. So the light does not go out of the medium. Okay, and this is made of ultra pure fused silica glassware. Don't worry about it. Basically, you think about it, say, light conducting material. So you will have the cores, okay, which is actually passing the light. Okay, you will have cladding and jacket. Let's look at the example picture. I think I'll talk about this. So this you all know, okay. You have the core and the clad. This is your basic fiber. This gets internally reflected. So the glass and plastic core, laser or light emitting diode on one side, and then you have a jacket specially designed on top of this to protect the thing. So out externally it will look like a thin wire on just with a plastic coating. Okay. But then I'll come back to that. So you see, if you make this very thin, the light will go almost straight. This is what is called a single mode fiber or SMF, commonly called SMF. Okay, and don't worry about this two graded index one. Let's just try to kind of make this slightly better. Okay, but if you give this thing, you are putting a light out here, multiple paths, then these multiple paths will take different times to go. Okay, so then I will again have a delay distortion out here. If I send something, I will get single mode, I will get almost the same thing. If I send this thin pulse out here, it gets spread out somewhere. Graded is just basically, rather than having two different refractive indices, it's kind of graded refractive indices. So it's you get this kind of gets flattened out a bit. So the delay distortion is less, but you still get a distortion. Okay. So you don't need to distinguish at your level between this and this, but the terms that you need to remember is SMF and MMF, multimode fiber and single mode fiber. Okay. Advantages of this is obvious. As I said, bandwidth is higher, which means, as we have seen, data rate is higher. There are calculations involving bandwidths and data rates and so on, but that depends on so many things. So most of these calculations kind of will assume very simple things. So I'm not getting into that. So data rates of hundreds of Gbps. I mean the calculations that we see in textbook. Okay, the actual real world things are obviously much more. They are smaller size. Okay, this is not really a great advantage. Lighter weight, it's okay. Lower attenuation, especially for single mode fibers and so on. Big point is electromagnetic isolation, because there is no electric current. It's light and doesn't get affected by any other, you have lightning and all, this does not affect it. Okay. Greater repeater spacing, tens of kilometers. Highly secure due to tap difficulty, this lack of signal radiation. Again, so some of you have heard about side channel attacks. Okay, so you send a 1, you're sending a voltage pulse. Okay, it will radiate something. You send a 0, nothing is being sent, will not radiate anything. So if somebody has a way of tapping the radiation, parts that he sees something high, can infer that there is a 1 being passed out there. This is kind of the idea. It's of course much more, but this is what is called a side channel attack. But since you have an optical light, basically you don't get any signal radiation like this that you can get. Okay, and that is an omnipresent now for most long distance communication, including telephone. So telephone is no longer transmitted as analog. Okay, it's transmitted as digital, converted to digital. And this is what I was mentioning, almost all long distance communication that you will see today. Actually, I don't know of any without that, basically. There may be some odd cases. Is optical fiber, digital communication. Okay. And as I said, single mode, multi-mode. Graded index you may read, but what you need to remember is SMF and MMF. MMF has different categories which kind of puts this thing out there. Okay? Different qualities of MMF person. So you see, also the attenuation will also depend on the material inside and so on. So you get different quality of things out there. And then this is something we'll not get into. Wireless is unguided. And you know, so the only thing that you may remember is the communication can be directional or unidirectional. Okay. For example, if you think about a microwave or satellite, is directional. You remember the disk or so on. So this is microwave disk and so on. You do communication, then there's disk that is receiving it. Okay. This will be, so microwave will not be like this. Microwave will be like this. Round things put on top of towers and so on. Your cell phone base stations are also directional. Okay, but there is some things that's going to be unidirectional, like, you know, if you think of a simple radio antenna, it's going to be unidirectional. So, and we'll not go too much into the physical layer things or micro, you know, this thing. So there are again different frequency ranges, and you talk about. So this maybe you may remember because your access points fall into this range. Okay, so they operate in the 2.4 gigahertz range or 5 gigahertz range and so on. So which is why your access points for the wireless, the antennas that use a direction. You need multiple antennas, you move them in different directions to radiate the thing field in different directions. Okay. Whereas radio waves and so on are unidirectional. So there are other issues that affect their propagations. Okay, who is affected more by atmospheric things? Some are straight line of sight things. So if the earth is this thing, or if a hill out there to get cut, like your cellular communication and so on. Okay. So this will not go into too much detail out there. Okay, so let me summarize. So what is it that we have done in this very, you know, kind of briefest introduction to communication? The first part, we have talked about some of the terminology like DB, DBM, basics of analog digital communication, okay, this Nyquist sampling theorem, things that you should know, the notion of spectrum, frequency, because you will deal with bandwidth, data rate all the time. In the next set of slides, when we talk about directly connecting two machines, we'll deal with signaling rate and so on. Okay. And then if you have a, you know, you're talking about these things, if you know the ranges of frequencies, you can figure out basically, if I send a signal power of this, or if I use two levels of signal components, what would be the maximum capacity that I can attain? You can try this out with your UTPs and optical fibers and so on. But again, from a practical point of view of what most of you will deal with, again, I want to be very careful here to not say the other side is important, okay? Because many of you will, if you go deeper, work in those areas, you will deal with them, okay? But most of you will kind of deal with the higher layers, and these things, these analog transmitters, digital transceivers, transmitters, okay? This changing the data, encoding the database signals and so on, things will be built for. They will exist. Okay. This more in the hardware basically, and mostly dealt with the communication signal processing people from electronics. Again, there is very important things that computer science engineering deal with. I don't want any misunderstanding to say that you will not work in this. Not important to know that. But given that this is one course, okay, and we cannot cover everything, we'll kind of focus on the higher layers. Okay. But these are things that you need to know. So the transmission medium part of it, okay, this you need to remember a bit, because you may not remember the exact values, but you need to remember the properties. Because as a network designer, okay, you will also have to design not just protocols and software, but the physical infrastructure for it. So take this example, which is what I'm, you know, kind of briefly do. Okay, suppose you think about that there was no LAN in IIT Kharagpur, no network. And you have to build a network. At the end of the course, I want you to think about this, because we'll put in more, you know, things in there. So you'll put in switches, this, that. How do you select switches and all, will come to them later on when we decide. Okay, but you will have hostels. Okay, now what does these hostels have? You have floors with wings in it and so on. So forth. All right, and then you will have, just think of only hostel and CIs. There will be academic buildings and other places. Okay, so you will have switches. The switches typically come in like 24 port, 48 port, and so on. And you will have to connect the LAN wire. Let us talk about wired LAN to each of the rooms. Okay, so there will be one wire here, one wire here, one wire here. So, given the building geometry, building length, what is the wire that you should use? Why can't I put? So if there are 12 rooms out here, okay. So if there are 12 rooms here and 12 rooms here, could I have put only one 24 port switch here? Are you with me? Yes, no?
Yes, sir.
Okay. Why do I need to put two? That is where the distance will come. You'll have to see from this switch what is the maximum distance of a room out here. That will depend on the geometry of the building. And remember, you cannot just, put a hole in the roof and take the wire through there. So shortest distance, basically. You'll have to guide it to something around the walls and so on. So then you need to know what kind of things to choose. Cost is a big factor because there are too many wires out here. Okay? So you need to know the properties of the medium. Whereas if you look at the hostel connection to CIC, okay, I'll probably have a couple of connections. So less number of wires, but larger distance. So this is less number of wires, larger distance. What is large? I will talk about. Okay, this is more number of wires, smaller distance. Okay. The next question is, what is the thing that each of these wires are carrying? What is the data that each of these wires are carrying? Anybody?
Digital data.
Yes, of course, digital data, but it's only now think practical now. Okay, but that's good. This digital data. Okay, all the LANs will carry digital data, but it's carrying data of one network point here to which one laptop or one desktop is connected. So the bandwidth that I need for this line, the data rate that this has to support is much less. Whereas this is collecting all the things from here and the entire hostel's data is going through here. So high bandwidth, low bandwidth needed. Right? Okay. So then I will go for low bandwidth, less costly, okay, things out there. So I'll go for an UTP. And this I will go for an optical fiber. First thing. Okay. What is this distance? UTP less than 100 meters. So if you find from your switch to some rooms is becoming more than 100 meters, you have to put a switch in the middle of that. Your switch acts also as a repeater. Okay. So UTP is good for 100 meters. Okay. Up to max, you want to support 1 Gbps rate. Okay. Whereas this optical fiber that I begin, because this is the bandwidth I don't worry about with optical fiber. It's just too large. Okay, it will depend. It will be constrained more by the switch ports at this end than the fiber. I'm just choosing the medium line. Okay, it will be higher cost, but then I have to run less these things. Okay, larger distance, as I said, typically if it is more than, actually normally if it is more than a few 100 meters. 100 to 100 meters, we kind of do this. 100, typically here is more than 100 meters. We don't use it. Hey, we don't use it. Are you with me? Yes, no?
Yes, sir.
Okay. Next thing is this one. Now this is all going inside your building. Okay. along walls and so on. This in open space. Okay. So typically we put it underground. Okay. But what if, okay, so what if this happens that there is a temporary event somewhere? Okay, and the nearest switch is here. This happens, we get this requirements. You're holding something in the ground. Okay. Or this building has just come up. It needs some network points. The entire thing wiring, etc. has not been done. So I want to draw a wire from this temporarily. Okay. So this wire I don't want to put OFC. We'll see OFC is another cost. I'm just choosing the media now, but there will be cost at this end, cost at this end, which will be higher than the UTP cost. Okay. So this temporary thing that I draw, I'm not going to dig the ground and put the temporary thing and so on necessarily. Okay. So if this is outdoor, okay, just think of that I've just drawn a wire, put over poles and just put it on the other building. Between two buildings in open space, cross the road and put in the other building. Will you use UTP or will you use fiber? Is it a good idea to use UTP? What do you think? You don't want to do this because outdoor, remember, is subject to impulse noise. And worst is, you have seen a place like Kharagpur, for example. Your design has to have to take care of a lot of things. Okay? It's a place where absolutely dry, storms almost never happen. It's okay. But here, lots of storms happen. There's a lot of lightning. And the lightning will not just corrupt your data, but that electrical interference will propagate to the two ends and burn the switches. So you never hang, but this is coming from the basic property of UTP. That's what I'm trying to say, which we have already mentioned in the slide. This high electrical interference. What is the electrical interference worrying about? Impulse noise. That is why you need to know about impulse noise. Okay. So you never hang UTP cables outdoor in a place like this. In a very cold place, you never hang UTP cables outdoors, because then if you have snow and all, the weight will increase. Ice will form on them and it will drop down. So again, no design is perfect. You balance many things, including cost. Cost is very, very important. I'll decide for how long. Is it winter when the chance of storms are lost and I need it only for 7 days? Fine, I'll draw one. Less cost. If it is for 1 month, I may draw an UTP, but I will put it underground. But if it's like, I don't know, if it's 6 months or 8 months, I'll do probably a fiber. But again, at this time, I'm focusing only on transmission medium. Okay. It will depend on other things like what is the switches on the other side and so on. There's cost there. When we talk about switches, we'll talk about that. So to finally summarize, just one sec. UTP up to 100 meters till 1 Gbps. Okay. As you increase the bandwidth, the distance goes down. Okay. With 10 Gbps, okay, this will be around 15 to 50 meters, depending on cable type. What are the cable types? Cat 6, 6A, 7, etc. etc. So with standard Cat 6, I think it's advisable not to go more than 15-20 meters. These numbers, if you talk to different people, will vary a little bit. But nobody will say this 15-20 nobody will say 100 meters, 200 meters. Even though theoretically, with 10 Gbps, you can go. Okay. Never hang outdoors. Never put too close to electrical lines. So when we do wirings on the wall, you will see that if there is electrical wire running, okay, we keep a 1 foot gap or something with it. Again, there are recommended gaps, but sometimes that is not always possible. At least put some gap. You just don't do it same way. Otherwise, sometimes the conduit is already there. You say, oh, there is space there. Why don't I run the LAN cable also through the electrical cable, side by side. Never do that. Okay. And with OFC, okay, shorter distance, few kilometers, or not even few kilometers, sorry. Multimode fiber, okay. It's like hundreds of meters. Okay. Longer distance, single mode fiber. Okay. Hundreds of meters to, I will check this and confirm tomorrow, next class. Few kilometers, depends, as I said, there are different qualities already. The base quality is around 300 meters max, as far as I remember. So this kind of guides you in when you want to build this network, and this is something, a case study that we'll take. Okay, we'll think that there is nothing in the IIT network. So right now I'm just choosing the media, but we'll see that there are other factors coming when we choose the switches later on, when we talk about switches and so on. Okay. Okay, I'm out of time. So we'll stop here. Is there any question? Okay, so if there are no questions, remember we have the lab there too. There are no questions, otherwise you can leave, class is over. And we'll meet again at 2 o'clock.